So, welcome to this class on hardware security. So, we shall be continuing our discussions on fault attack countermeasures. In particular, we shall be discussing about countermeasure which is an improvement over detection based countermeasures, or at least is a kind of an alternative strategy to detective countermeasures or detection based countermeasures. So, for example, right, what we will be covering in today's class is we shall be going into the infective countermeasures idea. We shall be seeing some of the differences with detection based countermeasures. We shall be seeing a proposal of a new detection based countermeasure, a countermeasure which is proposed, and then we shall discuss about some potential attacks on the detection based countermeasures using two different fault models. One of them is what is called as the constant fault model, and the second one is a random fault model, kind of similar to the differential fault attacks that we have already seen. And finally, we shall be trying to propose a modified countermeasure which would be secured against these type of attacks. So, to start with, I will start with a comment on detection scheme or detection based schemes which we already seen in the previous classes. So, the bias of a fault model, as we have seen, right, can be quantified in terms of the variance of the fault probability distribution, that is where we stopped, and therefore, right, we can actually control our fault induction in a manner so that many of the detection based countermeasures can fail, and therefore, they are vulnerable against practical attacks. So, therefore, right, we come into a new style of attack, new style of countermeasure which is called as infective countermeasures. So, the main idea behind infective countermeasures is to diffuse the impact of the fault such that even if the adversary were to attack the comparison step, the state would still be affected, and therefore, right, the state would still be kind of uncorrelated with the actual secret key. Okay, so, therefore, there is an inherent randomization which is kind of implicit in this kind of countermeasures, which tries to kind of make the output differential unusable to an attacker. So, therefore, there are some interesting or important differences with detection based countermeasures. The first is, like we have already seen that in the normal like the detection based countermeasures, we have the concept of an encryption or the actual encryption, and there is a redundant computation that you are doing. So, in this flavor of countermeasures, we shall bring in a third type of round which is called as a dummy round. Okay. So, the idea would be that between the redundant and the cipher computations, there would be a random number of dummy rounds which would take place, and the ability to detect a fault injection in any of the three rounds, which will be assumed that you will be assuming that the attacker has got the ability to detect a fault injection in any of these three types of rounds. That means the redundant round, the actual cipher computation round, and also the dummy rounds. And there is no explicit comparison step which is there, and therefore, right, we have seen in detection countermeasures we have an explicit comparison step where we kind of compare either you are doing whichever type of redundancy you are doing, but in this class of countermeasures there are no explicit comparison steps, and hence the adversary cannot attack the comparator itself without infecting the cipher state. Okay. So, therefore, the key point is that it avoids an explicit detection step by carefully embedding it in the infection process, and the effect of the fault is diffused in the ciphertext to render it unexploitable to an adversary. So, now we shall be kind of trying to see like one proposal which was published in a prior paper in FDTC in 2012, which basically gave a nice proposal about how an infective mechanism can be built. So, the idea is that so as we have seen that you have got the state S and you have got the state S dash, these are the two states which are there. So, the proposal basically kind of emphasize that for a good infective countermeasure or a sound or a secured infective countermeasure, it should have some kind of inherent randomization in it. The idea would be that suppose there is a fault, and as you can see that S dash is probably a corrupted state, and therefore, the differential between S and S dash is kind of is the infection. So, this is the infection which is essentially obtained, and this infection has to be diffused into the states. Okay. So, therefore, for this they use a diffusion function. The idea is that if this XOR essentially gives you a delta which is equal to 0, which means that there is no infection, then this function does not produce any non-zero output, and therefore, right, the output does not get diffused. On the other hand, when there is a disturbance, that means when there is a fault or there is a kind of aberration that you are doing to normal execution, then this function basically picks up that there is a disturbance created, and now it basically creates a random output, and this random output is basically diffused into the state. And if you do that, then the proposal kind of essentially ensures that, or tries to ensure that the output is not exploitable. And the output is not exploitable, or the output differential is not exploitable. As we have seen, right, when we talked about differential fault attacks, they essentially rely upon the fact that the one can, or the adversary can compute the output differential, and from there basically tries to extract out the key. So now the objective here is to make the output differential randomized or essentially uncorrelated to the secret key. However, we need concrete constructions, right, to realize. This is just a hypothetical kind of scenario where basically which gives us the idea about how to build infective countermeasures, and that seems to be not very trivial. Okay. So one of the proposals, and which is kind of a pretty popular countermeasure, is kind of sketched in this algorithm. Okay. And as you can see, right, this algorithm has got 3 different versions of ciphers. So there is one which is called as a state R0, which basically kind of stores the actual cipher computation. There is a cipher which is indexed by 1, okay, then that essentially is your redundant computation, and likewise there is a dummy computation. Okay, so now the dummy round, right, I will kind of elaborate what it means. It is basically something which is similar to the AES round, okay, but it does not take part in the actual encryption. So now again, like since we have got 3 variables, like our 3 indices 0, 1 and 2, so we will be again having like 3 ciphertext states C0, C1 and C2 to index the outputs of the cipher round, the redundant round, as well as your dummy round. So then we kind of index a variable I. So this is a kind of a loop index that we use, and we initialize it to 1. Okay. So now I will kind of like go through this algorithm in a step by step manner. You can actually read it from this reference as well. And the idea here is that there is a random bit generator which is basically producing a value which is lambda. So you can see that this loop index basically goes from 1 to 2n. That means I basically goes from 1 to 2n. The idea is that out of these 2n, there are n which are redundant rounds, and there are remaining n which are the actual encryption rounds. Okay. So now there is a specific order which is specified in this algorithm how these operations take place, and they are basically controlled by 3 variables. Okay. So the first one is lambda, which basically kind of tells you that the output is dummy round or whether it is not a dummy round. Okay. The idea is that if lambda is equal to 0, then it implies that it is a dummy round. On the other hand, if lambda is not 0, that means lambda is 1 because it produces a random bit, then it is either a cipher round or an actual round. So now we again use another variable. Okay. So therefore, right, this is shown here that I goes from 1 to 2n. Lambda is suppose 0. If lambda is 0, then this implies that it is a dummy round. Okay. So then we use another variable and we call that as say kappa. So when lambda is equal to 0, then kappa is equal to 2. Okay. And that is basically governed by this equation 6. That means kappa, as you can see, that when lambda is equal to 0, then it is I and lambda XORed with 2 of not lambda. That means like if not lambda is 1 and lambda is 0, then this part does not can come into effect, but this part comes, and therefore, right, kappa becomes equal to 2. So kappa is equal to 2, and then we use another variable which is essentially say tau, for example, and this tau, right, is equal to lambda into I by 2. Okay, and as lambda is equal to 0, in this case your tau is 0. Okay. So tau or eta, so you can use, so basically this is equal to 0. So likewise, like when lambda is equal to 1, and as we said lambda is equal to 1 means that it is not a dummy round, in that case kappa is equal to the LSB of I. So when I am doing I and 1, that means I am extracting the LSB of I. So basically, right, it would mean that like if I start with 1, then I mean I equal to 1, then LSB is 1. In the next case, when I becomes equal to 2, then LSB becomes 0. So it basically kind of alternates between 1 0 1 0 and so on. Okay. And therefore kappa is equal to the LSB of I, and then we have got tau which is equal to I by 2. Okay. So tau is in this case I by 2 because lambda is 1 and it is I by 2, but since I by 2 can be a fraction, what we do is we kind of seal this. Okay. So that means, right, it would mean that if I is equal to 1, then tau is equal to like 1 by 2, and that sealed. So 1 by 2, if you seal it, it becomes 1. Okay. So then it becomes 2 by 2, that means it becomes 1. So therefore in a way, right, this kind of repeats in this manner, that this tau, right, essentially is like something like 1 1, then 2 2 and so on. Okay. That means you can see that for every round, like this is the first round, this is the second round and so on, and finally, right, there will be like n and n. Okay. That means that is why I goes to I by 2, and when I is equal to 2n, we will have n here. So therefore, right, we will have a kind of repetition of this value of tau, okay, or psi, what as shown here, and this essentially is shown here. That means, right, you will basically do a computation here. So you will start with like a redundant computation. This is your redundant computation, and then there will be an actual cipher computation. Okay. So this is again shown here. So first you will do a redundant computation, then you will do a cipher computation, then you will do a redundant computation, then you will be doing a cipher computation. But then between a redundant computation and between a cipher computation, and between this, right, it may happen that lambda becomes equal to 0, and when lambda becomes equal to 0, then you do dummy operations. Okay. So therefore, what will happen is kind of depicted here is that you will be having like these kind of operations, and you can see that these are all dummy operations, and therefore, right, you do not know like what is essentially exactly happening. So from the side channel point of view, right, these are all indistinguishable, and like therefore, right, I mean what the adversary will probably see is the large number of rounds that will be taking place, but it will not be able to kind of distinguish whether it is a redundant round or whether it is a cipher round or whether it is a dummy round which is under play. And one point should be kept in mind is that it may be emphasized here that all the rounds are equivalent with respect to the side channel footprint by introducing dummy subbyte shift row mixed columns to the 0th round, because we know that in the 0th round there is just a key XOR. So we will be adding these dummy operations, and then the final round does not have a mixed column, so we will be putting in a dummy mixed column, and therefore we will have kind of 11 rounds. Okay. All of them are indistinguishable even along with the dummy operation. So now we have to understand how the infection takes place, and those are depicted here from equation 8 to 13 and so on, and that is what we will kind of discuss subsequent to this. So let me continue here. So therefore, right, I mean how does the infection take place? In order to understand that, I will kind of depict this with a diagram. So as I said that there is a redundant operation, there is a cipher operation. So what we do is, in order to understand that whether there is a kind of like fault which has been introduced, we will be using a special Boolean function, and that is called as SNLF, or abbreviating for some nonlinear Boolean function. A very common way to implement this would be by using the X inverse operation in GF2 power of 8, so that if there is a 0 input, that gets mapped into a 0 output. Okay. So therefore, right, you have got the cipher and the redundant rounds, and you basically XOR them and you feed it into an SNLF Boolean function. So now this is your proposed infective countermeasure, and as you can see, right, there are two types of fault infections that can take place here. So we basically, right, measure this difference between the cipher and between the redundant and the cipher by using this function. So the idea here is that there is this is your redundant computation denoted in C1, and this is your cipher which is essentially denoted in C0. The XOR between C0 and C1 is what is fed into your SNLF equation, and then, right, you see that if there is, the idea here is that for SNLF, right, the property is that if you get a 0 input, it gives you a 0 output. Okay. Whereas if you get a non-zero input, then it basically gives you a non-zero output. So therefore, right, the objective here is that if it gets a non-zero, like if C0 and C1 are not equal, for example, if C0 and C1 are not equal, then there will be an epsilon error which is basically getting produced, and that will be a result of applying this SNLF function to this difference. Okay. Note that this computation of epsilon will be effective when lambda is not equal to 0. That means not when when you are doing the dummy round operation. In fact, right, this computation will take place when you are doing the actual cipher round operation. Okay. That means if you are doing the redundant operation, okay, then it will not come into play, because remember that I, right, becomes is like 1, 2, 3 and so on, and if I is equal to 1, so you can see here there is also another additional parameter here which is not of I and 1. That means, right, if the LSB of I is 0, only then this part becomes effective. That means when I becomes even, only then this check is done. So this check is done only if I is even, okay. And remember, right, that I basically go something like 1, 2, 3, 4 and so on, and this is where like the actual cipher computations take place. So the check basically is done here at these alternate positions, and it is not done at every iteration, okay, or every increment of I. So then how do you diffuse this disturbance? So you basically diffuse this disturbance into these two registers R2 and R1, okay, and note that R2 essentially stands for the dummy operation and R0 stands for the actual cipher operation. So therefore, right, what we will do is that we will take this XOR difference, this will basically give me a non-zero difference in this case, and this will basically pollute my cipher operation, for example. However, when this is 0, that means if this is 0, then this is also equal to 0, and therefore, right, the cipher does not get contaminated. So this is the idea which is basically kind of applied over here to do the infection when there is a fault, okay. So therefore, in case of faults, the SNLF poisons the cipher state, okay. And actually, right, so this is it also poisons the dummy operation, as I said, that there is also a line which is R2 equal to R2 XOR epsilon. So therefore, the same epsilon is basically used to kind of pollute the dummy operation, okay. So thus after this, right, the dummy round state is not beta. So remember, so one thing I would like to also mention here is that the dummy round is initialized to beta, and therefore, right, when there is an error, then the dummy round, right, is essentially, right, because of this extra output of the SNLF, which is the non-zero output of the SNLF, if the initialization here is beta, that means if this is initialized to beta, and if you get a non-zero output here, then this becomes B plus epsilon or B XOR epsilon, and therefore the dummy round does not remain in its beta state, okay. And this is a very important point which will be which we need to keep in mind to understand the future discussions, okay. So let us see what is the consequence of these infections. And actually, right, there is also another way the infection will happen. For example, the fault can be also in the dummy round. So we saw here that if the fault is in the cipher round or in the redundant round, in the previous case what we saw is that there is an epsilon which is generated, which is polluting your cipher or it is polluting your dummy operation. It can also happen that a fault can be in the dummy operation, and if that happens, okay, so what will happen is that the redundant and the cipher rounds throughout, right, or following this will also get corrupted. So when, in consequence of whatever happens, like in the previous case, as we have seen that the fault was in the cipher or in the redundant round, because of which the dummy round got corrupted, or the fault can also be in the dummy round itself, and in both the cases we will see, right, that this difference will kind of propagate forward, okay, and will propagate and contaminate the future redundant and cipher round computations. So here is kind of a depiction of that. So if you see, right, if you see the algorithm, right, you will see that there is a line which basically does this operation. So this operation is nothing but it shows that Ck is equal to Rk XORed with C2 XORed with beta. So remember that this kappa, right, can be either 0, 1 or 2, okay. So in case when the dummy round is not corrupted, then this C2 content, right, or the content of this C2 is beta, and therefore what happens is that this beta gets cancelled with this beta, and therefore Ck is kind of Rk is basically assigned to Ck, okay. So therefore, right, in this case there is no problem. On the other hand, right, when this C2 is not equal to beta, then, right, this non-zero value here will kind of corrupt the corresponding round. That means whether it's a cipher round or if it's a redundant round, right, in both cases there will be a contamination. So therefore, right, this kind of brings us to the question, right, that what is the definition of dummy round, okay. So therefore, dummy round basically, right, as I said, that should be indistinguishable from the cipher round and from the redundant round, so that the attacker, right, by observing a side channel cannot understand that this is a dummy round getting into execution, okay, and therefore, right, it will consist of the same components as that we have in an AES operation. That means they will have a sub byte, shift row and mixed column operations. And what we will do here is that we will take an input which is a secret input beta, we will take a secret key which is K0, and such that this K0 is idempotent, which means like if I take beta as an input, this dummy operation also produces beta as output. So that if there is no fault, then the beta remains as beta, okay, and therefore right it never contaminates any future operation, because this, if C2 is beta, then beta always gets cancelled with beta and there is no future like contamination. However, if there is a fault, then this, as we discussed, right, then this dummy round output can get corrupted, and if it gets corrupted, then this C2 will not be equal to beta, and therefore CK will also be not equal to RK, but will get infected with an accompanying fault. So let us see like how this works like in more details. So basically, right, what will happen over here is that shown over here, that if this is beta and this is dummy is also beta, then I said that beta gets cancelled beta, so the redundant round does not get corrupted. However, if there is a non-zero value, then it kind of pollutes the redundant round computation. And likewise, right, so this is how, again, like you also have the cipher round also kind of getting contaminated if there is a non-zero value as a result of this dummy round getting either faulted or getting corrupted because of like a previous infection in a cipher or redundant round. One final point in this description is that there is, after you have done your like all your operations, that means you have come to your final cipher round, that means when your I is equal to 2n in your execution, you come to a compulsory dummy round. Okay. In this compulsory dummy round, you do this operation, that means you have got R0, which is basically storing your actual cipher output. You XOR it with round function R2, K0 XORed with beta. Remember that if there is no fault, then R2 has beta here, and therefore again this results in beta, and therefore beta gets cancelled with beta, and therefore R0 remains as R0 without any problem. However, if there is like a fault in R2, and because of that like there has been a previous fault in the cipher or in the redundant round, because of which, as we know, that R2 is not equal to beta, and therefore right this will result in something different, kind of random, and that will basically get XORed with beta, will produce another random, and that will lead to another level of infection that will happen in the cipher operation. Okay. So therefore, right, this is kind of the overall description, but unfortunately, right, this particular countermeasure can be attacked. Okay. So the first attack that I will be discussing here is essentially due to a work which was published in AVTC in 2013, which showed like that infective countermeasures are more difficult to construct than believed. Okay. So for example, right, the fault F, so we will basically assume that the fault F is in the first byte of the second row in the input of the 10th cipher round of AES 128, and therefore, right, if you remember that in the normal execution we always have like when I becomes equal to 2n, so we finally end with the cipher round, because previous to that there has been somewhere where we have done the redundant round. Okay. And it may happen that within this, right, there are some number of dummy rounds. Okay. So I do not know that whether like how many dummy rounds has actually taken place. So here we are assuming that the fault F is in the first byte of the second round at the input of this 10th round cipher, that means before the final computation has been done. Okay. So therefore the countermeasure will infect the faulty computation twice. Okay. The first time it will execute is after the execution of the 10th cipher round, and the second time, right, because there is a compulsory dummy round, so that also will kind of lead to the infection. So there will be 2 times that we will have an infection. So let us see like how that works, and here is a depiction of how that works. So as you can see that the fault is in the 10th cipher round, so R0 is equal to round function R0, K10, and here is the fault. The fault has been shown over here. This is the first byte of the second row, and that has been faulted by value and showed here as F. And because of the shift row, right, essentially this will get shifted, this error will come here. So this epsilon is nothing but like, because suppose the original state here was I110, okay, and in the actual computation, right, this will be I110 and S applied on that, and in the faulted computation, right, this I110 will be XORed with F, and then we will be doing an S box. Remember that the redundant computation in the 10th round has already taken place. The redundant run is done, we are basically doing the actual cipher round, and when you are doing this, there is a fault. Okay. Because of this fault, and this is the 10th round cipher, this computation, right, if I say that this is my reference point R1 and I am basically calculating R0 and there is a fault. Okay. So you basically see that there is a fault over here, and because of this fault, right, you will basically have an infection. So let us see like how the infection will basically look like. So therefore, right, you will have like for example what will happen is, if you remember this diagram, in this diagram, right, there is a cipher which is being computed, and this cipher is nothing but like the XOR of the output of the SNLF function. So as we know that there is an error which is being generated. So therefore, if we get epsilon over here, like if we get epsilon over here, then this will basically generate an SNLF epsilon, and this SNLF epsilon will basically get XOR. Remember that already you have this infection epsilon, and that will get augmented with SNLF epsilon, and so you will have epsilon XOR with SNLF epsilon. Okay. So also remember that there is this dummy round like over here, and because of this dummy round there will be a further effect on the dummy round operation. So this initially, right, this dummy round has beta. So if I take an XOR of beta with R2, so this, right, was kind of generating 0 over here. I mean beta XOR with R2 was 0, but because of this infection SNLF epsilon, this will come over here, and therefore, right, it will affect this particular byte as well. Now remember that this round function, right, is just a normal, like a normal AES encryption or round, and therefore there will be a shift row operation, and because of which, right, this will get shifted and it will kind of affect this column, okay, shown here as delta 1, delta 2, delta 3 and delta 4. So now if you take an XOR between these two things to understand what is the final differential which you obtain, you will see that this kind of gets shifted over here. This error, which is epsilon XOR SNLF epsilon, gets exposed to the attacker. So the attacker is able to see this diffusion even now, okay, and therefore, right, the attacker can start guessing the key, and from there we will try to kind of reduce and obtain the actual key value. So this exactly is basically the idea behind the attack, and we can see like the more details of the attack as follows. So therefore, what we will do is basically, right, this infection will kind of result in a differential like this, and as we know the corresponding key, right, to this is shown over here in the last round key and shown in red, that is, this is your K13 for example. So therefore, now if I basically like know this differential, so this differential means I will know the value of epsilon XOR SNLF epsilon. Remember that this SNLF is something like an X inverse function, and therefore if I know this, right, I will get some possible values of epsilon, okay. So therefore, right, what I will try to kind of do from here is that I will basically attacker, what I will basically do is I will use the value of epsilon. Remember that epsilon is nothing but the error, and that is basically, as we have seen, is equal to S of I110 XORed with F XORed with I110, okay. So this is where I wrote here epsilon is equal to S of I110 XORed with F XORed with S of I110, okay. So if you know this, right, then you basically what you will try to do is you will try to make hypothesis on I110, okay, and from there you will basically try to gather the value of or obtain the value of K1311, which is this key, okay. So therefore you will, of course you will not get a unique value, so therefore you have to repeat this process with two more pairs of faulty and correct ciphertext. But remember, in this case that the fault model is constant, because if the fault model is not constant, then this F will give you multiple values, and there could be like 256 possible values for this F, and therefore, right, you will not get any reduction of entropy, okay. So therefore, right, this will not lead to the reduction or revelation of the key. So therefore, what we will be trying to do is we will basically try to keep this fault constant, and from there we will try to come up with a solution which will give me values for I110, and hence will leak me information about K1311. So one of the restrictions behind this attack, right, is that this attack is kind of restricted to the last 3 rows of the 10th round, and it will not work if the fault is there in the first row, for example, okay. So why will it not work can be easily observed here, and this is the question, like if the infection is in the first round, then what will happen, okay. So why will it not work? So this will not work, and this is kind of elaborated in this work in 2014, and that essentially can be easily observed if you again see the depiction of what happens if the fault is over here. So if the fault is over here, like previously we will have an infection and this will propagate, and we will get, so this fault is again at the input of the 10th round, 10th cipher round. So therefore what will happen is that this will get be epsilon XOR SNLF epsilon. This will this is the result of the cipher round infection, and likewise there will be a dummy round encryption infection, and that is shown here in this column, like alpha 1, alpha 2, alpha 3 and alpha 4. So now if you take an XOR between these two things, remember this is the this is the effect on the dummy round, and this is the effect on the actual cipher round. So, if you take an XOR, because remember that there will be a final step in the equation where there is an effect of the compulsory dummy round. Okay. So, the compulsory dummy round will again pollute the actual cipher round. So, therefore, this differential will get mixed with the cipher differential. Okay. And this will result, this shown here as this step 14, which will basically give you the final output differential. Okay. Now, this differential, if you observe, you see, right, is showing here values alpha 1, alpha 2, alpha 3, alpha 4, which trivially I have got no idea about it. Okay. So, they kind of looks pretty much random. And if they are random, you can see that this epsilon, Zod epsilon, which I was previously able to see quite clearly, is now getting kind of mixed with this alpha 1 value, and therefore, I cannot like segregate it, I cannot separate it out from this infection. Okay. And therefore, right, I cannot make like hypothesis of the I110, and which essentially led to the revelation of the corresponding key byte. So, therefore, right, the attack will not straightforward work, and therefore, this attack at this point we can just do like reveal these 12 bytes, but the first round I will not be able to leak, and one of the reasons why this will not work in the first round is because of the shift row operation. If you go back and just see like the state transfer happened here, this got exposed because this column, right, essentially is like getting shifted here. You can see that this differential here is getting shifted because of the shift rows, and therefore, right, this particular thing is not affected, it kind of gets exposed. On the other hand, right, it does not work over here because right here in this particular state, in this particular transformation, remember that in the first round there is no shift. Okay, and therefore, this byte does not get shifted, and therefore, this column overlaps with this column. Okay, and therefore, this gets hidden, and therefore, it does not leak. So, this is the basic idea behind the attack, and like we will see, remember that it still works on only 3 bytes, and it does not work on the first row. So, we need to kind of do something so that we can kind of extend it to a solution which works on pretty much the entire state matrix. We will also see another extension where we basically kind of relax the fault model and make it work on random fault models. Okay. So, I will stop here, and we will continue from the next class on this point. Okay. Thank you.